My name's Evan Olson, and I'll be solving problem 9 from chapter 11 of the Fundamentals of Heat and Mass Transfer 8th edition. The problem statement says that there is a novel heat exchanger concept which consists of a large number of extruded polypropylene sheets which each have a fin-like geometry and are subsequently stacked and melted together to form the heat exchanger core. Besides being inexpensive, the heat exchanger can easily be recycled at the end of its life. Carbon dioxide at a mean temperature of 10 degrees Celsius and a pressure of 2 atmospheres is flowing in the cool channels at a mean velocity of 0.1 meters per second, and air at 30 degrees Celsius and 2 atmospheres flows at 0.2 meters per second in the warm channels. Neglecting the thermal contact resistance at the welded interface, determine the product of the overall heat transfer coefficient and heat transfer area, UA, for a heat exchanger core consisting of 200 cool channels and 200 warm channels. We can first look at the diagram that was given to us by the problem and find that each channel for CO2 and airflow has a size of 4 millimeters by 11 millimeters. This allows us to calculate the hydraulic diameter, which is going to be used for our Reynolds number calculations. And the hydraulic diameter is defined by 4 times the cross-sectional area of each channel divided by the perimeter of each channel. And that gives us a hydraulic diameter of 1 millimeter. In order to find the Reynolds number of our fluid, we can use our density times the mean fluid velocity times our hydraulic diameter divided by our dynamic viscosity. And to find the density and dynamic viscosity of our fluids, we can use our lookup tables at each fluid's mean temperature and pressure to find the density, dynamic viscosity, and thermal conductivity, which we'll need later. Plugging into this equation for both CO2 and air, we find a Reynolds number of 13.33 for CO2 and 25.56 for air, and that is within the laminar flow regime. Now that we know that the fluid is in the laminar flow region, we know that our Nusselt number is going to be a constant, and that is defined by our B over A ratio, which is the ratio between the length and height of our fluid pipes. And given a ratio of 2.75, that results in a average Nusselt number for each fluid passage of about 3.81. We can then use this Nusselt number correlation to find our average heat convection coefficient for both CO2 and air, which is defined by the Nusselt number times our thermal conductivity of the fluid divided by the hydraulic diameter. And for CO2, we get a value of 57.15 watts per meter squared Kelvin, and for air, we get 99.06 watts per meter squared Kelvin. The final goal for this problem is to calculate the UA value of the heat exchanger, and the UA value, or shortened, we can find our U value first. That's defined by 1 over the total thermal resistance, and that is excluding area with the 2 primes. And to find our total thermal resistance, we need to know the thermal resistance, or the thermal circuit of the system. And we can just sum up all of the different resistances that we can find throughout the problem. First of all, we have the resistance to convection from our fluid to the wall of both the CO2 channel and the air channels. That's just defined as 1 over the convection coefficient times our channel cross-sectional area for both CO2 and air, and that results in a value of 0.0175 divided by our channel area, Kelvin per watt for the CO2 channel, and 0.01 over our channel area, Kelvin per watt for the air channel. We additionally have our resistance to conduction within the wall, which will be the width of the wall, which is the C value, defined right up here in our diagram, C, divided by the thermal conductivity of the wall times the area of the channel. And that gets us a value of 0.0235 over our channel area, Kelvin per watt. And then we sum all of that together to get a total resistance of 0.0511 divided by our channel area. The reason we are isolating out this channel area in our resistance solution is because we don't know the total contact area of these channels for the heat transfer to occur. If you can imagine, these channels extend out in 3 dimensions. The heat transfer is occurring on this 3-dimensional surface rather than just on the 2-dimensional one. And since we don't know this full depth into the page, we have to solve this in terms of the area. But we know that our U value, we can just divide out the A and turn this into a resistance flux. So our UA value was originally 1 over R, the total resistance. But if we divide out the A, this turns into U equaling 1 over R times A. And since we have A in the denominator of our R, this will end up canceling out in the solution, and we'll just get 0.0511 Kelvin per watt. And then in this equation, now we have a resistance flux. We can find that value to be 19.561 watts per meter squared Kelvin. In order to get our solution into as little terms as possible, we can try and solve for our channel area in terms of L. Since we know that our channel area, or our heat flux, is going in between these channels and not up, since these are the same fluid, our channel area is just going to be B times L, as is shown there. And we know B times L is 0.004 times L, since B is 4 millimeters, and we have 400 channels, so that turns into 0.004 times L times 400, which gets us a total area of 1.6 L. If we multiply this into our U equation to find our UA value, we get a final UA value of 31.29 L watts per Kelvin.